Welcome to part 2. We are on 2c and still differentiating. So here we have a log base 3. So we need to remember that the derivative of natural log of x is 1 over x. I think we had that already. The derivative of a different base, so a log base a of x, it's kind of the same. But then we also multiply by natural log of a on the bottom. Okay, so here we have h prime of x is, we're going to have on the bottom natural log of 3 times x squared, and then this is going to be a chain rule. X squared is the inside function, so we need a 2x on the top. And then my second term is just going to be a negative 7. Next page. Part D, still differentiating. So we need to recall that the derivative of some random number to the x, just like e to the x, we get an a to the x term back, but then we have to multiply by natural log of a. Okay, so here we're going to have f prime of x is, we have 7 to something, so natural log of 7 times 7 to the 3x. Then we're using the chain rule. 3x is the inside function, so we need to multiply by its derivative, which is 3. Over here we've got a 3. E to the something stays the same, e to the 8x, but it's chain rule, so we need to multiply by the derivative of 8x, which is 8. I'm going to leave that unsimplified, as is our pattern. Okay, number 3, we have this profit function. That's going to be a total profit. We want marginal profit, which is the derivative, p prime, so we're taking a derivative. So p prime of x, the derivative of 2x is just 2. Minus 0.3, and then for this part I'm going to need a product rule. The x is my first guy, the natural log of x is my second guy. So I've got the first guy times the derivative of the second guy, plus the second guy, natural log of x, times the derivative of the first guy, which is just 1. The derivative of x is 1. So that is 2 minus 0.3, these x's are going to cancel. 1 plus natural log of x. It's okay to leave the answer like that, but if we distribute, we get 2 minus 0.3 minus 0.3 natural log of x, which is 1.7 minus 0.3 natural log of x. That's p prime. Okay, how many thousands of pencils should be sold to maximize profit? Remember, when we maximize, the first step is to get critical values. Of course, we're looking for an absolute maximum here. So we want to set p prime equal to 0. That's 1.7 minus 0.3 natural log of x is equal to 0. That tells me 1.7 is 0.3 natural log of x. That tells me that natural log of x is 1.7 divided by 0.3. This tells me that x is e to the 1.7 over 0.3, which is approximately equal to 289.07. Now I need to make sure this is actually a maximum and not a minimum or something. I only have one, and we have a theorem that says if you have one critical value, it's either a max or a min. An absolute max or an absolute min, not just a relative one. So let's see. I'm going to use second derivative to see if that's really positive. I mean, really a maximum. So p double prime of x, I'm taking the derivative of this. The first guy goes away. So it's going to be negative 0.3 over x. Notice when I plug in this x, the 289.07, I get a negative number. Negative double prime, negative second derivative, tells me I'm concave down. So it's really a max. Make sure you show me this calculation, otherwise I won't know that you know that it's a max for sure. So my answer is 289.07 thousand. Okay, my next question is about exponential growth. Whenever you see inflation, you can assume we're talking about exponential growth. And it says Manhattan was worth $24 in 1626, and that's a typo. It should say merchandise. Okay, so the value of Manhattan at a given time is going to be its initial value, that's the $24. E, we need a rate, here's my 5%, 0.05 times t, where t equals years since 1626. So my value today is for 2014 minus 1626. Which is 388. So that's going to be equal to 24e to the 0.05 times 388, which is going to be approximately $6 billion if you type that in your calculator. You can write down the whole number, or you can just write down a couple of digits followed by the right number of zeros, or you can write it like I did, 6 billion, or you could write 6 point whatever billion. As long as I know what you mean, I'm okay with it. And as long as what you mean is correct and you said it in a way that it means that. Okay. Next problem. Number 5. The number of applications for patents grew dramatically in recent years, with growth averaging about 4.6 per year, and they give us this equation. Whenever you see an equation like this, it means you have exponential growth, and this value is the rate. So I'm going to write n of t equals, it tells us to start in 1980, and the initial value was 112,000. And here we have the rate, 0.046 t. Okay, so in 2020, we need to subtract 1980 to get the number of years since. So we have n of 40, which is 112,000 e to the 0.046 times 40. $112,000 times e to the 0.046 times 40. 705,212. Okay. Estimate the doubling time. There's two ways to do this. Well, there's three ways. If you want to really work it out, you can, but the formula for it is natural log of 2 divided by the rate. That is approximately 15.07 years. Or I'm okay if you want to use the rule of 70. Then you do 70 divided by 4.6. That is 15.22 years. This one is more accurate, but I'm fine with either way you want to estimate it. Okay, number 6 is a present value problem. The actor is going to be paid $12 million in 3 years, and he thinks he can invest his money at 6.2%. The main thing to remember about present value is that it's always lower, because having money now is more valuable than having money later. You don't need as much of it to have the same value. If you had less money now, you could invest it and at the end of the 3 years have the 12 million anyway. So these things are just like interest, continuously compounded, except negative. So the value at time t is going to be my sort of initial value. In this case, it's actually my final value. E to the negative, here's my rate, t. So the value of money in 3 years, of 12 million in 3 years, is 12 million e to the negative 0.062 times 3. Which is about $9,963,000. Remember, they should always be lower. Present value is always lower. Sometimes this rate, 6.2%, is called the discount rate. That might help you remember that it's lower. All right. In problem 7, after winning the lottery, you want to set aside enough money to retire in 40 years. I guess what you're going to do is set enough money aside to retire and then blow the rest of it. That's fine. If you'll need $5 million to retire comfortably and can earn 4% a year, that's very conservative, compounded continuously, how much should you set aside today? This is the exact same problem as the previous one. It just has a different rate and a starting value. So the value at time t, we want $5 million e to the negative 0.04 t. We don't have to set aside more than $5 million to have $5 million in 40 years. We need to set aside less. That's why it's negative. Same as the previous problem. So here we're using 40 for our time. E to the negative 0.04 times 40. So we have I get about $1 million, so I have $1,009,000 approximately. I kind of rounded off in the middle of the number. There's some digits down there, but that's ridiculously precise.